All right, let's do some work. Recall that work equals force times distance. Write that out. Where the force is in the direction of the motion. So when we're looking at this problem, we have a force of tan of pi over 4x. So we'll have, in general, actually I'll set that up here, we'll go from a to b of f of x dx. So in this particular problem, we'll go from 0 to 1 of tangent of pi over 4x dx. We have the derivative of the inside would be pi over 4, so if I put that over here and then I put 4 over pi, or you could do a substitution, we don't need to, equals 4 over pi times the antiderivative of tangent would be negative ln of the absolute value of cosine of pi over 4x. And we'll evaluate that from 0 to 1. At this point, we just go through and do all the calculations. So we'll have 4 over pi. Let's take out the negative as well. Ln of the cosine of pi over 4, that's going to be a positive number. We don't need the absolute value, minus the ln of the cosine of 0. So we get negative pi over 4 times the ln of 1 over root 2. Sometimes that's a more convenient form to use. Should put in there, that's minus ln of 1, which is just 0. That can be simplified to negative 4 over pi times the ln of 2 to the negative 1/2. That negative 1/2 can come down, so we get 2 over pi times the ln of 2. So that would be the amount of work done with that force from 0 to 1. Let's take a look at this next one. So we have last summer the construction workers needed to move a cart of 200 pounds to the top of the roof of the gym, 70 feet high. The cable holding the cart weighed 4 pounds per foot. How much work was done to move the cart and the cable the 70 feet to get up there? So there's two aspects of this. We have our work is going to be approximately equal to taking that 200 pounds and we want to lift that straight up the 70 feet. So we have the cart part, 200 pounds times 70 feet. But now we have this rope. And the thing about the rope is it's changing constantly. Right? Because as soon as you get part of that rope up, that's done and we don't need to worry about it. So let's see what would happen if we look at it in pieces. If we kind of think of, here's the cart, and we're going to be moving it up. Let's say, you can say there's the top of the gym just to make it something simple. We'll cut it up into segments, and we'll deal with those segments, and then see what happens with that. So how much do we need to lift? We need, at the beginning, we need to lift 70 feet of it. What's the weight of all of that? We have 4 pounds per foot. And then we're going to be moving we're going to break this up right now into a 1 foot section. Right? All we're doing is breaking it up into pieces, and then we'll go from there. So once that one is brought up, then we have how much is left. 69 feet. The weight of that is 4 pounds per foot. And again, we're going to have a 1 foot section. We need to keep on going. I'll leave that just to separate that out. Plus, we have 68 feet of rope. That'll be 4 pounds per foot times that 1 foot section. Plus, you can see where this is going. We keep on going until we get down to that last foot, and we have 4 pounds per foot, and it's just 1 foot there. So right now, that's an approximation for our work. How are we going to get a better approximation? We can make the section smaller and smaller and smaller. So what do we need to do? We need to find that the length is going to 0, or in other words, the norm is going to 0. In fact, just go ahead and write that over here. We let the norm go to 0, so this thing becomes 200 pounds times 70 feet. So there's our cart, plus the summation, all of this as the norm goes to 0, which gives us our exact value of 0 to 70. Now let's see what's going on here. We have 70, 69, 68, etc. In other words, it's 70 minus what the, and we'll use y here since it's going vertically, 70 minus the y value times 4, because it's 4 pounds per foot, and then times this section, the width of the section we're dealing with, dy, and as we're going, that delta y, as it went to, norm goes to 0, that's going to dy. And so that's not an approximation at this point, that would be the exact work. Then let's take a look at units on this. I think this part's fairly clear. We have pound feet. Over here we have the 70 minus y, that's going to be feet. 4 is pound feet. And then dy will be feet. So we still get that same thing. We're dealing with pound feet. And it should look somewhat familiar in terms of those experience with it when you're looking at Newton meters. All right, and the rest of that you could finish. That's not a terribly difficult integral for you to do. Right now I want to focus on just doing the work. All right, let's take a look at a fish tank. It's 5 feet tall, or 4 feet long by 2 feet wide. Let's put a comma there, by 5 feet tall. Water weighs 62.5 pounds per cubic foot, and the tank is initially filled with water. So part A, find the work lifting all the water out of the tank. Then we're going to find the work if the water is lifted 6 feet above the tank. Find the work if the tank is only partially filled with water to a height of 3 feet. So let's start by kind of taking a look at a picture here. Go ahead and sketch that. Mine's a little off. I made that top part a little too big, too wide. It's all right. So what we're going to do is the similar thing. Here's our tank. We have 4, 2. We're going to make a slice of it. And we're going to look and see how much will it work to take to lift that slice out. And then we'll do another slice. And another slice and another slice. For convenience sake, what we're going to do is we'll just make that slice 1/6 of a foot for right now, just to go through the steps so we can figure out what's going on. So what do we have? The volume of each piece will be the base area times the height of slice, right? That thickness of that slice that we're taking. So if we look here, we can say our work is going to be approximately equal to, we're going to say our volume would be 4 times 2, and again, if I use that 1/6 for that height, what are the units of these going to be? This is going to be feet cubed, right? Because each one of those will be in feet. Times the weight. So if we compare that to the previous problem, we were given that it was each part of the rope was 4 pounds per foot, and right now our weight for this one would be 62.5 pounds per cubic foot. And if we take a look at that bottom piece, we're going to have to raise it up 5 feet. That's our first one, and then we'll look at the second one because we're going to be starting from that bottom. We're going to have a similar setup. Oh, let's kind of take a look at this. We have the volume times our weight. That's going to be our force. And then what's the 5? That's our distance. So similarly, we'll say 4 times 2 times 1/6. In fact, what can you say each time about the volume? Each one of these slices will be the same thing. We'll also have that 62.5 pounds per cubic foot. Slide that over. Times, this time we don't need to move it the whole 5 feet. It's 4 feet, 4 and 5/6 feet. Since that's 1/6 less. Let's do one more slice. Just to make sure we have it, 4 times 2 times 1/6 cubic feet. We have 62.5. Let me fix that. 62.5 pounds per cubic foot. Times, this time would be 4 and 4/6 or 4 and 2/3 feet. And then we'll just go all the way down to that last one. 4 times 2 times 1/6. Again, cubic feet times 62.5 pounds per foot, cubic foot. And then the last piece that we would have would be 1/6. So that again is our approximation. What are we going to do? We're going to let the norm of the slices there, that thickness that we're taking, go to 0. And we will get the integral from, let's go our work, integral from 0 to 5. Now why 0 to 5? Because that's the amount of water that we have in there. And we have 4 times 2. Now this 1/6 came from the thickness of the slice, and that norm's going to 0, so that's going to be our dy. So I'll leave that part off right there, and I'll go 62.5 times, how do we deal with these numbers? 5 minus what our y values are. And then we have our dy. So what about part B? Part B says we're going to go 6 feet above. Now in that one, so we want to take each one, when we're, instead of lifting it out of 5, we're going to lift it out to 11. And then if we looked at that next one, taking a slice, it'd be 10 and 5/6, and then 10 and 2/3, etc., all the way down to 1. So instead of redoing all this work, I'm just going to write there, and we'll say that work equals, we still have the same amount of water in the tank, so it's 0 to 5, 4 times 2 times 62.5 times, how much are we lifting it this time? We're going to go 11 minus y dy. And let's look at the last one. So the last one says we're going to start with 3 feet of water. So when we're looking at it, we will have 0 to 3. And we're going to bring it to the top of the tank, so that's basically the same thing we did in the first one. So we'll have 5 minus y dy. And that makes sense when we're looking at it. We say 5 minus 0, that bottom one has to be lifted up a total of 5, and the top part of that water is only have to be lifted up 2. And when we're looking at all of these, it would end up being, when we can see the units here, although I didn't write the feet on that one. We have cubic feet reduced, so we again will have pound feet for our units. All right, let's go to the next one. All right, again, there's always construction going on. So a bucket needed to be lifted 16 feet to the second floor of the E building. The bucket weighed 2 pounds and was initially filled with 5 pounds of water. However, water was leaking from the bucket at a constant rate so that only 1 pound of water remained after it moved up 16 feet. Find the work done lifting the bucket and the water. Now, since this is leaking, it's changing constantly. So we're going to go about doing this in the same way. If there was no leak, then it would be quite simple. We could just say, what's our total weight? We have a bucket's 2 pounds. We have 5 pounds of water, so we have 7 pounds, and it would be lifted up 16 feet. So we could just multiply them, and we'd be done. But alas, we have to deal with that leak. So let's see what's going on for there. On this type of thing, since it's a constant rate, it'll end up being a linear equation. And when we write this equation, we are in charge to set where the origin, what's our reference for all of these numbers. And we want to make that the easiest way possible. So what we can do is say, since it's going vertically, we'll deal with y again. When y equals 0, that force, the weight, is going to be 7 pounds. When y gets to the top, 16, that force will be 3 pounds. Just to make sure it's all clear, it's 7 pounds because it's 2 pounds plus 5 pounds of water. And at the top, there's only 1 pound of water, and the bucket's 2 pounds, so that's a total of 3. So since this is a linear relationship, all we need to do is find the equation of the line. The slope equals 3 minus 7 divided by 16 minus 0 to get negative 4 over 16, or negative 1/4. And we already have the y-intercept, or the intercept, I should say, the force intercept in this case. So we can say f of y equals 7 minus 1/4 y. That is our force equation. So what we're going to do is same thing we did before. If we took some slices here and then summed them all up and let the norm go to 0, we're going to end up getting that work is going to be done. We're going from 0 to 16 of the force 7 minus 1/4 y times dy. And the last one deals with what we've already seen before, Hooke's law. So I'll just briefly go over this. Hooke's law says that when you're dealing with the spring, you can say your force is going to equal to some constant times x, where we have this is our constant, and this is the distance stretched beyond the natural length. So in this particular one, we have 10 pounds of force are required to stretch the spring to a length of 12 inches, but it's 8 inches long, so it's going 4 inches past. So we'll have 10 equals k times 4, so k equals 10 over 4, or 5 halves. So that gives us our force equation. Force will be 5 halves x. Now we need to stretch this. We need to stretch it from 6 inches to 15 inches. So we'll come and say, starting at 0, sorry, that's a typo. That should be from a length of 8 inches to 15 inches. So we're starting at 8 inches and we're going to 15 inches. So in other words, it needs to stretch out 7 more than its natural length. And then we have 5 halves x dx. And again, these integrals are not so hard. It's just that, can we set them up, right? We're applying the same idea that we've been doing. We find one slice, one section. We let the the norm of it going to 0, the thickness of the slice, whatever the case, or the amount of rope that we're talking about. We let it go to 0. That gives us our exact volume or exact work, depending on the situation. And then we can set up our integral because we let the sums are going to the exact value. And that's it.